In this lecture, we'll be continuing with our treatment of limits, and we will discuss the limit laws. And these are the laws that we use to do limit calculations. But it's important to recognize that each of these laws, and we'll go through them, is derived from the definition, the formal definition of limit that we gave previously. I encourage you to look in the textbook at the derivation of some of these to see how this works. And you can think of this as, it's like driving a car. Using these laws is like using the steering wheel and the pedals, all the ways you interact with the car, but the underlying engine, which you don't have your hands directly on when you're driving the car, but you know it's there driving things. That underlying engine is the definition of limit. That being said, here we have the first law is constant law, and this is the simplest one. If your function is just a constant, some constant c, then the limit as x goes to a of that function is the limit as x goes to a of a constant, which is just whatever that constant is. Intuitively, x is not involved at all. There's no x involved in this constant value, so that limit doesn't affect things at all. It's just the constant itself. For the sum law, and it's important to note for this law and the ones that follow it, this only holds if the limit as x goes to f of x, as the limit as x goes to a of f of x equals L, and the limit as x goes to a of g of x equals M. We need both of these limits on their own to exist as a precondition. But if that's the case, then the limit of the sum can be split into the sum of the limits. We have a similar result for products. As long as the limits of f of x and g of x exist on their own, the limit as x goes to a of the product of f of x times g of x is the product of the limits, the individual limits. Same kind of rule for a quotient law. The only key is we have to disallow division by 0. So if the limit of g of x is non-zero, then the limit of the quotient is the quotient of the limits. We also have these two laws. Technically, there's some redundancy here, but we call one of them root law because we use it quite extensively. If you're taking the nth root of x, if that's your function, limit as x goes to a of the nth root of x, then that will be the nth root of a. And the way you can think of this is that this is achieved by bringing the limit inside the nth root. And the limit as x goes to a of x is, of course, just a. More generally, we have this substitution law, which basically says if everything is lined up, so think of g as the inner function. If that function, as x goes to a, is approaching L, so out here in this composition, the inner part is approaching L, but then the limit of f as the inner part goes to L, that will be f of L. So think of it this way. As x goes to a, this g of x is going to L, and so the whole thing is going to f of L. Another way to think of that is we are bringing this limit inside of f. So as long as both of these limits exist, the limit as x goes to a of g of x is equal to L, and the limit as x goes to L of f of x is equal to f of L. As long as these two work, then we can bring this limit inside. And we will use that also extensively. So these are best understood by doing some examples. And in a homework, you would never have to show this level of granularity, but let's illustrate how you're actually using these rules here. So we would compute this by first using the sum law. We would break this limit into the limit as x goes to 4 of 2x squared minus the limit as x goes to 4 of root x plus the limit as x goes to 4 of 1. And so this would be our sum or difference law, in this case the difference. And this works actually because each of these limits on their own will exist. Now we know from our constant law that this limit as x goes to 4 of 1 is just 1. And again, intuitively, the fact that there's no x here means that this limit doesn't affect that value, doesn't affect 1. 1, as a constant, doesn't care what x is doing. Here, so this is our constant law. And here we can use our root law. We can bring the limit inside the square root. Here, and then I didn't state it in this way, you can factor a constant out of the limit, and you could write this entire expression as 2 times the limit as x goes to 4 of x times the limit as x goes to 4 of x. And this would have been our product law. We then can evaluate these. The limit as x goes to 4 of x is 4. The limit as x goes to 4 of x is 4. So this becomes 2 times 4 times 4 minus the square root of, and again, the limit as x goes to 4 of x is also 4 plus 1. And so we have 4 times 4 is 16 times 2 is 32 minus square root of 4 is 2 plus 1 or 31. Again, if you were doing a question like this for homework, you can interpret what we did here as what people will often just call direct evaluation of the limit. So this number, 31, is what you got if you plugged 4 in for x. But it's important to, and you can do that. Functionally, you can just plug it in, but it's important to realize that when you do that, when you directly evaluate the value, plugging in the value for x, what you in fact are doing is using all of these different limit laws to do the calculation. So direct evaluation, plugging in that value of 4, is using these laws, which is using the definition of limit. Again, you can directly evaluate. This is an exhaustive demonstration to really drive the point home that we're using all of these different laws that we just went over when we're calculating this type of limit. Let's look at another type of limit, and let's think about the graph. So the graph of 1 over x squared will have a vertical asymptote of the positive y-axis. And so we know our graph looks like this. So the issue now, think about the idea of limit. The limit, as x approaches 0 of this function, we're honing in. Let's start from the right. As we hone in from the right on 0 for x, the function is taking off. It's getting arbitrarily large. The same is happening if we hone in from the left. The function is getting unboundedly large. And we say, in this case, because 1 over x squared gets arbitrarily large, as x approaches 0, we say the limit is infinite. Now, that's a special case of the limit not existing. So there is no limit. According to the limit definition, there is no limit. But we do often say that in this case, the limit is infinity because you have different ways that a limit cannot exist. And this is a case where we have this infinite issue. And by the way, one way you can think of the reason this is blowing up, think as x goes to 0, think of a tiny number. So 1 over a billion. 1 over a billion. Well, 1 over a billion squared is even tinier, but it's in the denominator. So the whole thing would be 1 billion squared. And that's why this thing is blowing up. And again, we'll say the limit is infinite, again, which is a special case of the limit not existing. We'll look more at questions like this in future lectures as well. Let's do some other standard calculation examples. So let's do this limit question here and think about the laws that we use. And the first thing that we do is recognize our root law. Our root law says we can bring that limit inside. So this is the square root of the limit as x goes to 3 of x squared plus 91. Then we can use our sum law to say this is, underneath the square root sign, the limit as x goes to 3 of x squared plus the limit as x goes to 3 of 91. Then we can write that x squared as the limit as x goes to 3 of x squared. And that we could actually call our substitution law. Because what we did was bring the limit inside of x squared. So it might be, I realize this isn't changing things, but it might be easier to think of it as there's your parentheses. And so this limit was brought inside the square, the squaring function. And we also have that the constant law, 91 is just a number, just a constant. It doesn't care what x is doing. So our constant law just says that limit is 91. Then, of course, we have this limit as x goes to 3 of x is just 3 plus 91, 3 squared, which is 9. And so this is the square root of 100, or 10. And again, this is a explicit solution where we show what the limit laws that we're using are. But remember, this is the shortcut for this is what people often call direct evaluation. If you just took 3 and plugged it in, you would have, for x, you'd get 100, square root of 100, or 10. But it's important, again, to recognize when you're doing these limit questions, you are explicitly using these limit laws, which are using the definition of limit. So again, in a homework or an exam setting, you don't have to write all this. It's fine with you just saying by direct evaluation, but it's critical to understand that you are, in fact, using these limit laws when you do that. We'll try another. So for this example, And this time I won't write all the steps. Maybe we'll do, well, rather than I won't write all the laws, but we'll write many of the steps. So we can use the root law to bring the limit inside the square root. But then if you look and try and directly evaluate, if we plug 3 in for x, we would get 9 minus 6, which is 3, minus 3, which is 0. So we would have a division by 0 if we tried to evaluate directly. And recall, we had seen an example similar to this before. What we want to do is factor that denominator. And it looks like we should have, what, x minus 3 times x plus 1. So the denominator factors in this way. And then we note that we can cancel the x minus 3's. And so this becomes the square root of the limit as x goes to 3 of 1 over x plus 1. And we then would use quotient law to say this, what's in the square root sign would be, and I can just write it so that we see it explicitly. This would be the limit as x goes to 3 of 1 over the limit as x goes to 3 of x plus 1. So again, this would be by our quotient law. Then we would say in the numerator, constant law tells us that this limit is just 1. And in the bottom, we would use the sum law to say we have limit as x goes to 3 of x plus the limit as x goes to 3 of 1. So this again was our sum law. And now this limit as x goes to 3 of x is 3. From constant law, this other limit is 1. Or the square root of a fourth, or 1/2. So this is an example where we couldn't actually do direct evaluation without doing some algebra first. And so we needed to get this denominator factored for this to work. And again, you don't necessarily have to show all this, but it's important to make sure that you understand it. Understand that when you do this type of evaluation, you are in fact using the limit laws. One thing that's important in your written work, whether on an exam or in a homework, is you need to make sure to always be writing the limit expression. You can't omit that limit expression. That is, this limit expression here always has to be written. There's a tendency to want to be kind of lazy about writing things and omit it, but you should never do that. You should always be very precise in the way that you write this and explicit. And so you should always be writing your limit signs in each step.